which will be from Niloy Mitra. So Niloy is a professor at Niloy is a professor of geometry processing in the Department of Computer Science at UCL. He received his master's and PhD degrees in electrical engineering from Stanford University, advised by Leo Gabus and Mark Levoy, who was postdoctoral researcher with Helmut Pottmann at Technical University of Vienna. Niloy's current research focuses on shape analysis, data-driven geometry processing, computational fabrication. He is also especially interested in developing structure-aware representations and abstractions involving 3D geometric data to help reason from raw images, videos, or scan data. And over the course of his career, Niloy received lots of best paper and career awards from Eurographics, BMBC, and Siggraph. Today, Niloy will give a talk which is entitled Generative Models for Vector Graphics. We can see your slides. Please take it away. Thank you.
Thanks, Natalia. Can you hear me okay?
Yes.
Yeah, we start 10 minutes after. So is it okay to go a bit over? Like I'm supposed to finish at 45.
Yeah, it's okay. Try to catch up, but we can go a bit over. Thank you.
Okay. Thanks everyone.
By the way, I think the slide is in presenter view. If you want to change it to.
Is it the way? How do I change this? Just check.
Yeah, there's a button up right, I think.
Yeah, I think I will switch the. Because it's sharing this window. Anyone knows it?
Can you try to play the presentation again? I think there was maybe a button.
Okay. Yeah.
Yeah. That one more to the right, where your mouse is. At the bottom. Yeah.
Right. Yes. Yeah, okay. Yeah. That was hidden for the Zoom.
Yes.
Okay. Thanks, Andrea. Okay. Good afternoon, everyone, or morning if you are in a different time zone, morning or evening. So today I'm going to once we can generate programs, as we'll see, we can also how artists typically create models. So in industrial design, they would start with sketching objects. And if we follow how the artists are taught to sketch, they start with drawing scaffolds and then shaping the objects by different sort of primitive operations. And many of the research in geometry processing where we try to extract abstraction is trying to find these types of primitives. If we look at the CAD modeling world, which is a computer-aided design, which is a method of choice for most designers, they're using a variety of operations. And if you have used Maya or if you've used Autodesk, it's calling through this various sequence of operations, calling a primitive, editing the primitive parameters, and in the end, we get a high-quality 3D geometry that is typically meshed out. That is a language that many of the fabrication models know how to use, so it can directly be sent to printers and others. This quickly gets quite crazy. So here's an example. You can look at it on YouTube, the actual video creation. So this is a 3D artist, an expert artist, really expert artist, creating this model, and this is a screenshot of he or she creating the model. And you can see it's extremely complex how they are modeling. In the end, we get this complex structure graph, which is a sequence of operations. So you are supposed to read these graphs from the left to right. So from the left, these are the operations, and the nodes denote how the operations sort of operate on the primitives they connect to. Right? So all this geometry can be seen as a program. So if we can recover the program, it would be really good because we can translate. So last year at Siggraph Asia, we showed that it's possible to interpret Sketch into these programs. So from the input on the column B, we can infer the programs as you see in the middle, and then we can read it out as the CAD model on the right. Now, but there's a huge restriction of our method because this is an interactive system, which means the user can model one of the red operations or the orange operations at the time. So this does not scale, and I'll explain why that's a problem. So this is an area that's getting a lot of attention now. So this year at Siggraph 2021, Autodesk released this incredible Fusion 360 dataset where each model comes as all the sequence or the sequence of operations that generates these models. And now you can train your favorite sequence operator, whether it's RNN or a transformer, as David was talking about, to create these type of generative models that directly output instructions. And you can see some of our recent Siggraph paper looking into this aspect. Now, to summarize, we would like to get programs from sketches or from 3D models, but in this talk, I will talk about 2D sketches because that's complicated enough. And we are not going to produce things on the left, but things as you see on the right. So essentially, we are going to output the program that would infer this. So this works to a good extent if we have training data. But what happens if we do not have enough training data? And that's the domain where we want to go, and that's the theme of this workshop. So the first thing is, where do we get our training data from, and in what form? Right. And here we would use our graphics knowledge because we know how the projection modules work, how the rendering modules work, how the procedural sort of functions work, and we'll try to differentiate through them. The second problem is more important, that even if we had outsourced and managed to get a huge amount of training data in terms of procedures, the procedural models are not unique. By that, I mean different procedures can give rise to the same final shape. And that is a problem if we are trying to do a sequence to sequence model. It's possible to get around that problem, but it's better if we can do something differently. And then, as you will see, what is a good representation for these types of problems? Already in today's workshop, we saw sign distance field, we saw meshes, point clouds, and videos. So I've seen a variety of them, and not surprisingly, they would also come back here in this context. Okay. So the first one I will talk about is Im Vec work that we presented at CVPR earlier this week. And the other one is a NIRIPS 2021 paper that I will present. And both of them are done by Pradyumna, who's a PhD student in my group, along with collaborators from Adobe and UCL. Okay, so let's go into this problem. I really like patterns and at this fonts. So here's a sequence of like fonts, which are artwork on the left, icons, which are middle one, or even animation sequences, which is, I just unrolled it on the right. Right? So these are all vector fonts. Just to give a highlight of what we are expecting to do, we are expecting to output these type of results, which when seen through an interpreter of this language would produce a shape like this. Now, to highlight how complex the problem can be, so for example, what would be the sequence or program for this? We would expect our method to output this language. Okay, so that's our goal. And already we see that the output that we expect to see is very sort of irregular in structure. Right? There's not a regular structure, so we have to get around that. Okay. I assume that we can solve the problem, and all the talk I will go through that, but let's see what we will expect to benefit. So if we want to interpolate in the latent space of programs, we would not get a result like this. So here, what we see here is a quality we would expect if we do an image-based representation, which is a pixel-based representation, and it is hard to have explicit control on the underlying structure. So we'll come back to these interpolation results later on using vectors or using programmatic approaches. Okay. So this is now, we are not the first to look into this problem. So there's a couple of very interesting relevant paper in this domain. One is this SVG VAE, another is this deep SVG. that produces vectors or produces SVGs, particularly, and which can support like arbitrary rescaling to a target resolution size. So all the nice advantages there. The problem is they require explicit training in terms of vector fonts. So all these fonts had their corresponding SVG operations available, and that's a problem we are trying to, or that's a requirement we are trying to avoid. Okay, so let's summarize what we expect our algorithm to achieve. We want it to perform well without having explicit vector supervision as input. But we do want the output to be vector or output to be programs, right? And what we also want is having an end-to-end trainable module so that we can supervise this, as we will see, with images. Right? And earlier, Andreas talked about the Platonic GAN, and when we worked on the Platonic GAN paper, that's when we realized that it's nice if we can supervise with different modality. In that case, we supervise with images, trying to recover 3D or voxel information. So we are continuing the theme here. So let's look at the architecture. I would focus on the most interesting parts of the architecture, but let me walk you from the left to right into the main modality. So the first one, and the main important part would come, which is the path decoder, but I'm jumping ahead of myself. So let's start with the main block. The first block is very standard, and each of you can come up with your own favorite way of doing it. We take an image, so this is a pixel image, and we want to encode and come up with a latent code, right? So you can have a convolutional approach to come up with the latent code, or MLP even, so you can decide that. Because we have unknown number of segments explaining the final shape, so we don't know how many lines we will have in the SVG. For that, we would use a RNN-based approach. Okay, so this is a sequence. At that time, we used RNN. Now we might want to try the transformer approaches, but the relevance or the relations are quite local at this stage, so RNN might just be fine. And now let's go to the most interesting part, which is the key ingredient that makes it work, which is this path decoder module. Okay, so this would output vectors. Now, what this path decoder does is the following. So it takes a latent code, which is coming from the RNN, and this is, as you will see in the end, it's end-to-end supervised and end-to-end trainable, no supervision, sorry. So what we are trying to do is each of the curve segment, we assume it to be a deformation, unknown deformation of a circle. And the circle is, it's not like circle in the geometric sense, it's topologically a disk. That means it's connected back, it loops back into itself. And it can be filled, because we are talking about filled curves here. So in this, in the top one, you see the yellow blob. That's a closed sort of blob of a circle that has been deformed, the black one. And if you see a thin curve, that means it sort of loops back into itself. So it goes and comes back. Right? So that's how a circle can be deformed. So any of the closed curve can be deformed from a circle. And what the network is supposed to give is this deformation of these each point. Right? So there are a couple of very interesting and important points happening here. One is the order of the points are going to be known, because that's how we sample the points. We would have some extra bits to denote if it's going to be looping back to itself. And the third point is, because it's a closed disk, we propose to use a circular convolution here, so that the neighborhood is kept aware of the ordering. And this output becomes the parameters of a Bezier path. I refer to the paper for the details of how we map the points into 4 points of the Bezier curve. Okay. Now, at this point, we have a vector output, but we have to compare with the image. Luckily, with the prior works we did, so we had a Siggraph paper back in 2020, and at the same time, there was a paper by Lee and colleagues who produced a differential compositing block. Right? So all it does, it makes the composition differentiable. And the main ingredient there, it does a soft assignment there instead of an explicit raster one. So it blurs out that kernel, and that allows it to be end-to-end differentiable. Okay. And now this whole thing can be trained together. Right? So we can train on input raster images, and what it produces in the end is a latent code, which is this red or orange block here. That is the latent space where we can operate on. At the same time, it produces this individual segments, which are the vector output, as you will see here. The compositional block does not care about which line or which curve goes where. It only cares about the final one. So it's a bit like PointNet. It's oblivious to the ordering of the curves. Let's look at some of the results of this block of what we have here. So these were all trained of images with 128 by 128. And as you see on the lower one, the right ones, the blue and the green highlighted one, are our results. So you can see the reconstruction results. Because we output vectors, you can zoom in. And if you see the pixelated versions are if it's an image-based representation, or sorry, a zoom in of the original input image. But on the right is what we get because we have a vector output. So we can keep on going higher and higher in resolution, because we will just resample the output vector graphics. So that's good. So that's an even more zoomed up version of that. And let's look at how the interpolation starts to look here. And this gets quite interesting. So if we do an image VAE, that would be the top row, and ours will be the bottom row. Both are trained with images only. And if you see on the top, there are these pixelated or aliasing that gets carried through, and it looks quite reasonable though, but it doesn't look reasonable when you zoom in. You start to see the pixelation. With my graphics eye, it bothers me a lot. If you look at our output, so these 9, the way it is represented is by a big black sort of circle that has been deformed, and a blue, but actually it's white. I just show blue for clarity here, which is composited on top. Right? So that's how it creates the hole in the middle. So it's a composition of 2 curves that you see here. Okay. Good. So this outputs 2 lines, and also along with which comes on top. That's given by the ordering of the composition block. Okay. Because it can be trained only with images, it can be used directly for MNIST. And Yasuda showed some results on MNIST datasets. So this is also trained on the MNIST dataset. And now you can see the advantage of having the vector, because you can zoom into this resolution. You know that MNIST dataset, the image sizes are particularly small. So the super resolution artifacts are a lot higher. Here are a few more examples for different fonts, as you will see here, and some of the artifacts you see with the jagged lines, will come back to that soon. Now, there are 2 nice sort of fallouts of our method. One is, because it's RNN based, we can increase the complexity of the method by giving it more number of RNN blocks when we do the loop unrolling. Here, by going from 6 curves to 7 curves to 8 to maximum of 12 curves across the whole data set. And you can see that the network learns to add more and more details at the parts where it needs to, in this case, the horizontal line on the 7. The next one is particularly nice because we have a correspondence, because we have an order on the circle points. We get a correspondence for free across the data set. So it's unsupervised correspondence finding, and the color or the gradient of the color denotes correspondence as you go along the row, each of the row, whether it's fonts or emojis and others. There's a couple of limitations. One is because it's supervised with pixel information, we can sometimes miss small parts. Here, the inside of the 4 is particularly important semantically, but it's missed in the output. Or if we have very complex topology, here the 6 doesn't quite touch in the input. So we can't represent this anymore as a composition of 2 closed curves. Here it could not find and the right reconstruction and causes some problems. And this topology problem is what inspired us to go to this next paper, which got accepted now for NeurIPS, which is this multi-implicit neural representation. And it has a couple of really nice insights that I want to talk about today in the remaining time. Okay, so if we look at fonts, so now we are not looking at emojis, we're just looking at fonts. Right? If you look at font families, there are a lot of font artists whose whole life's work is coming up with fonts. And they have a couple of interesting criteria, and we have all used fonts in our daily life. So one is we have these fonts which have a lot of character, as you see here. But then if we look across the fonts, there's a lot of style variation. So if you look at the highlighted A here, if you look between the first and the last one, I think the French and the third one is a Gothic one. There's an incredible stylistic variation in how A is represented, but also how many curves are there, what are the type of corners, what are the type of things. And in our vision world, this would be what would be a right template that would represent all these fonts here. Just to slow down here, please recall that our goal is to come up with these programs, and we want to come up with these methods that would eventually translate to 3D. And that's why we want to pick a problem domain which we expect the methods will translate to 3D when we go there. And in terms of programs, this is our vision that that's what will happen. The other thing is, although there is a lot of variation across the different styles, inside the same sort of characters, the fonts are consistent. So if you look at the French style, the highlighted green one, they all have the same style, the same with Italian, and the same with Gothic. And that's our notion of font families, right? And our goal is, can we identify these sort of decoupling of the type, which is which character it is, A, B, or C, versus the style, which is the name of the font family, right? Can we learn this directly in the network? So that's our goal. Okay. And like before, this would allow us to go in increasing resolution without having aliasing artifact. That should be understood quite easily by now. The output would again be a collection of splines. And we would not go into how this would compare to raster-based methods, which was the image VAE that I presented early on. We saw the artifacts. Let's just quickly recap the vector weights alternatives. So the resolution independence we already achieved before, and also the SVG VAE and the deep SVG had it. However, as we saw in Im Vec, we could not handle very complicated fonts. So we could not handle the Gothic font, we could not handle the 6 and other things, right? So that's what we want to address in this one. Right? So what is this multi-implicit? So let me talk about that multi-implicit. The goal is threefold, that we want a method that allows to generate programs for complex shapes or complex fonts in this case. So you can zoom in arbitrarily. It allows to capture sharp features. So let's quickly go over the type of sharp features so that we are all on the same page of the complexity of the problem. So one are the sharp features where it transitions from black and white. That's fairly clear. But another one is the type of these corners, and these are quite diverse, as we saw when we go across font families. We can have very different corners, and what is a good representation that would allow us to have corners. Okay, and then we want to work with minimal supervision, and I'll talk about what this minimal supervision would be. Okay, so what we start with is the following. That this is architecture, but I will break it down into the most important part that we want to look at. So this is the part which is the key module, and the key sub-module of that is the corner template. But let's first talk about the multi-SDF and the corner template. These are related. So what is a SDF? SDF would be a sign distance field, but in the context of fonts, and I'll talk about that. The other modules are the standard sort of gradient loss we will have on the L2 regularization and the shape loss. So these are quite standard. You can have a VAE, then you would have a normal or a KL divergence on the Z term also. That's a standard detail here. Okay. So here, what we are going to work on are sign distance field of the font. So instead of a mesh here, we have a font boundary, which is denoted by this white line, and then we have a SDF around that white, both inside and outside. Okay. And this can be resampled at arbitrary resolution. Again, that's an advantage we had before. So this is fine. But when we pass the gradient, what we observed is that it doesn't get, like for point samples close to the 0 level set or close to the white iso surface or iso curve on the left, the gradients get very hard to propagate. So what we did in this case is, instead of working on these SDF fields, we worked on these anti-aliased SDF fields. And the interesting part here is we used a known anti-aliasing kernel or a filter kernel. So it's very similar if you make the connection that when we looked at the platonic GAN or we look at the block GAN or hollow GAN, there was a known camera module that was fixed through which we backpropagate. In this case, this rendering module or the camera module becomes the anti-aliasing module, and that's known and fixed because that's the imaging module we are used. And when we pass the gradient, it sort of collectively gets information from quite a few neighboring pixels at the same time without us having to consider SDF values very far from the 0 level set. So this really speeds up the convergence. For the exact kernel choice, we looked up some old literature from graphics to find standard modules there. But that's a fixed module. That's not optimized for. And then we are fine to only do importance sampling or get more samples from near the 0 level set. So we don't have to sample from the black regions, right? So it really speeds up convergence. And if you look at deep SDF and other works, there's the same idea of sampling near the 0 level sets because that's what we care about. But with this additional anti-aliasing term, the gradients gets a nice, better behaved. There is another problem. So that's the SDF aspect of the problem, but now we go to the multi-SDF. But first, let me talk about the problem. The problem is if we work with these SDF images, when we get to the corners, then the aliasing effect starts to dominate. And that means that the learned vector graphics would have a lot of wiggly lines that would represent the images, but not actually the programs that we are trying to output. So here's quite a clever trick that I really like. So what we do is, instead of outputting a final SDF, we output simple SDF. That means we are saying complex SDF can be expressed as a combination of simple SDFs. And what is simple SDF? SDF coming from simple curves. So in the left, there's two simple curves, the two black curves, curve 1 and curve 2. And then the quadrant 4 or Q4 on the right can be expressed as a composition of these two SDF with the right sort of sign choice, what's plus and minus. And this type of sharp corners can be supervised, or can be, the loss function only needs to look at it locally, which is a huge advantage, as we will see soon. So to summarize this part, we can represent corners, which are complex SDF, as superposition of simple SDF. Again, the SDFs are not supervised in the sense that the user doesn't have to provide the SDFs, the algorithm will infer, or the network will infer these SDFs. Okay. I think this would make it clear. So here's on the left is a font F, on the right is a reconstruction F, as you will see here. I'm just trying to calculate the time, how much extra I have. I think I should be done in 5 minutes. So if you look at input and reconstruction, this looks pretty sharp, and it continues to look sharp as you go up in resolution. Okay. Now, the real question is, what did the network find in terms of this individual SDF? And let's look at that, right? Or I'll give you a few seconds to imagine how you would represent these Fs as composition of simple SDFs or simple curves. It shouldn't be quite obvious because I'll be disappointed if it is. So these are the individual curves, or these are the, after we take out the isosurface, this is what the network finds. And because we have the composition with the right signs, this is what it gets. So now you see, although the individual curves look quite chaotic, when you look at the combined one, we start to see what's really happening. Around the corners, it does its crazy things, but it has the right sort of mix of plus and minus to get the corner sharply, right? And this was not, so now try to imagine that if we had to get this individual curves as supervision signal, I would not know how to even collect such a data set, right? But this we can do directly with direct only corner level supervision. Corner level means we have a corner detector that tells to zoom in the corner part, and then the network finds out what are the individual curves and what is the combination modules of the correct plus and minus to get the right shape. Right? And this is a very, very clever sort of way of setting up the problem that Pradyumna came up with that I really like, and it works quite well, as you will see here. Okay. In terms of the other things, these are quite standard. I would not go too much into that details, except for the gradient loss, because the individual SDFs are, or these are SDFs, so you can have an iconal loss on the gradient that it is indeed a distance field, but that's a technical detail. Okay, let's see the result. Does it really do what it promises to do? So the second column is image VAE. Deep SVG result is there. Im2 Vec is what I presented in the first half of the talk, hours as you see here. And this continues to be nice as we go forward. So the pink zoom is the multi-SDF method, or the multi-implicit method I just presented. Okay. Let's look at some interpolation results. So now it gets really crazy, and these are quite crazy fonts we found. So if you do Im2 Vec, which is the method I described in the first one, then the latent space for these crazy signals, it's really difficult for it to find something reasonable. And this is why we went to the multi-implicit form. Here it gets a reasonable output. And if you look at the zooms of the endpoints, again, the bottom row, the pink are the outputs of this multi-implicit one. It does reconstruct the corners quite nicely with the supervision that we discussed. Right. Now we can do our standard tricks we do with GANs, so or a generative setup. So we have a generative setup. Now, given an input glyph, which is one font, can we find the rest of it? And I think to this audience, I don't have to explain this much. So what we need to find is we freeze the network and optimize for the latent code that will match this. So we need to know that this is the letter A. So we look for a latent code Z, fixing the network that minimizes the loss. And if we do one step or a few gradient steps, this becomes nice. And now we have a particular Z, which is a Z star, and that then I can take and read out the output for the other fonts like B, C, D, etc. So this allows to take a single one and reconstruct the font, right, for this one, which is particularly advantageous, and something we at Adobe also quite like, because part of our business is to work with fonts. They keep vector output. These are snaps from the paper, so they are pixelated, but actually the output is vector, so it's not pixelated if you had looked at the program. You can also do with a partial one. So it's a partial input. It's the same problem with mask. So there's nothing surprising. It still continues to work quite nicely. And we get the sharp corners. The sharp corners are coming from the underlying latent space and the multi-implicit formulation we have. because it's only works with this local supervision around corners, it can have some spikes if we go to ridiculous zoom. So this is after you zoom at very high amount of zoom, you would start to see some spikes. And on the right, you see the overlay of the multi-implicits. At a similar failing, we can have these slightly wobbly one, again, if we go at very high resolution. Okay, so that brings to the end of the talk here. I tried to make up for the sum of the time. So the main agenda here is to work with a data set where we have a lot of access, in this case, images, and to output programs, which is what we see in the middle. And in the process, we had to design the network, but in the end, as a reward, we get nicer interpolation behavior, because now we are restricted to the interpolations in this language space, which means all these interpolations, say, removes cubic splines or removes like operations that are available in the SVG library. So in a strange way, that the whole approach is regularized by the choice of languages or the choice of operations we have. In the modeling scenario, this would be the choice of CAD operations we have, and that's something we are working on. And hopefully we'll be able to present results in the 3D context later this year. So with all the code available, both for the first work, the Im Vec, and also this multi-implicits is available on the GitHub page. And the papers are available on our geometry website at QCL, and I'll be happy to take any questions at this stage. Thank you.
Thank you, Niloy. Great talk. I also love how it's a little bit different from the mainstream line of research we've ever heard about so far. We need to go to the panel, but before we do that, maybe just to reconnect back to the topic of our workshop, could you reiterate on your longer term vision, how you think about extending this methodology to, I don't know, modeling, like full 3D modeling, maybe even articulated objects, rigs, blend shapes? Like, do you even think that that's the right way to do it?
So we have the results, but I can't show you because it's not out here. So this is how the change would be. So in the CAD sequence, so whether the input is an image sketch or a 3D sort of scan, the inferred one, the third column would be the output, which is the program again, right? And so the part that needs to be changed is a compositional model. So it's not going to be 2D rasterized anymore. It has to be like in 3D. We are not working through a camera module. So the eventual longer term goal would be that we don't even have 3D models to work with, but we work with like images of that. But that even links to linking with the Platonic GAN work we have done earlier on. But I think that's too far in the future. For now, I'll be really happy if we can work with 3D models without part supervision to come up with corresponding CAD sequences that can produce these ones, so, without having supervision on the CAD instructions. Right. So I think that without the supervision of CAD instruction is the critical part.
Got it. Okay, thank you so much. Thank you for the great talk.